Welcome to Scientific Notation Introduction. So this is an introduction to Chapter 1, the first chapter of the book. We're going to talk about calculators and exponential notation. So calculators are useful tools for us, but when you use exponential notation, you're going to make fewer mistakes if you do as much of the math in your head as possible. Right? So you are smart. Your calculator is not smart. Your calculator does exactly what you tell it to do, which means if you make a mistake plugging something into the calculator is going to give you the wrong answer, and you're not going to know. So you should try to do as much of the math in your head as possible. Once you get some practice at this, you'll become faster than you would plugging into the calculator, and you'll make fewer mistakes. So the majority of Chapter 1 does not require a calculator and can be done just using your head. So attempt each of the problems without a calculator first, and then use a calculator to check your answer. So let's talk about some terminology with the notation. Often in science, we use very large and very small numbers. For example, a drop of water contains roughly 1.5 sextillion molecules. Right? So that's a lot of zeros. We don't want to have to write out all those zeros because, again, we're probably going to make a mistake counting them or writing them down. Another example is that an atom of neon has an empirical radius of roughly 0.000000070 centimeters. So again, that's a lot of zeros. So we have very large numbers like this, we have very small numbers like this one. We want to have a way of writing these numbers down. Number one, that doesn't require so many zeros so that we are less likely to make mistakes. And two, just because it's just difficult to read and deal with numbers that are this large or small. So, numbers that are expressed as regular numbers, like 42 or 0.057 or the numbers on the last slide, these are in fixed decimal or fixed notation. Those are regular numbers. But very large and very small numbers can be more clearly expressed in exponential notation. So this is a number times 10 to some integer power. So a drop of water contains roughly 1.5 times 10 to the 21 molecules. This is a lot easier for us to work with instead of having a string of 21 zeros after the 5. An atom of neon has an empirical radius of roughly 7.0 times 10 to the minus 9 centimeters. Again, this is easier to work with instead of having all those zeros in there that we have to count and write every time we want to write this number down. Values expressed in exponential notation have 3 parts. So for some example number like this, negative 6.5 times 10 to the minus 4, we have the negative sign in front. That's the sign. The 6.5 is what is called the significand, or the decimal, or the digit, or the mantissa, or the coefficient. The 10 to the negative 4 is the exponential term. And the base is 10. The exponent, or the power, is negative 4. So we've got the sign, the significand, and the exponential term. The exponential term is made up of a base and a power. So the book uses the terms sign, significand, and exponential to refer to these 3 parts. I will generally use the terms sign, coefficient, instead of significant, and exponential, or base and exponent, sometimes base and power, to refer to these parts. So it's up to you to remember what exactly I mean when I say sign, or significant, or coefficient. I'm going to use coefficient most of the time, or exponential. And note that there's a difference between exponential and exponent. Okay? Exponent refers just to that part. Exponential refers to all of that. So be very careful and listen very carefully whether I'm saying exponent or exponential. Those are 2 different things. So that was Scientific Notation Introduction.